Welcome back to the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode 36, where today we have a live episode. We have Parker here, just came back from Ottawa to Toronto.
That's right, and right now we're actually in the McLennan Physical Laboratories, where we take our physics courses here at the University of Toronto. So enjoy the episode, and we'll see you guys soon.
See ya.
It's the language of the universe.
But I don't understand it.
Welcome back, everybody, to the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode 36, where today we are actually talking about something that we go through almost every day of our lives here in university: logic and proofs. So what we're going to be getting into today is not like too technical, because I know like a lot of people, especially us in first year, we're super scared of proofs.
That is very correct.
So we're not going to get too technical, but we're just going to kind of help you guys understand the basic kind of language of mathematics and how logic and how these quantifiers and everything we're going to talk about today just help you, understand math.
That's right. And the title of this video is Q.E.D, right? And we're not talking about quantum electrodynamics.
No, we're not. No, we're not.
We are actually going to talk about proofs in logic, as we said. But Q.E.D, what does that mean? It means Quod erat demonstratum. And if you didn't know,
it's in Latin.
Yeah, it's Latin, and abbreviated to Q.E.D. Some people put that at the end of their proofs. It roughly translates to like quite easily demonstrated.
Yeah, quite easily demonstrated. I knew it as quite easily done. So I mean, I guess it's basically the same idea. It's just telling you that the proof is over, and it was easy. It's kind of like a joke at this point.
It's kind of a flex because you say like, okay, I'm gonna prove to you this.
Yeah.
I do the proof and then quite easily demonstrated.
So yeah, it's kind of like you're saying, this was a very easy proof for me.
Yeah, but also you can put a little box, which is what I usually put, or you could put two diagonal lines to show that the proof is over. Or I also write sometimes proof done. Just, quite simple.
Any way to show that the proof is done.
That's
right. Basically it. So yeah, that's where we get the Q.E.D from. Name of the video. Just a small introduction.
Yeah, so the first thing we're going to talk about are sets.
Sets, let's get into it.
I think sets are basically the most fundamental concepts. That you need to understand, and what makes an element a part of a set. Yeah. And so we're just going to discuss that right now. So the first example we want to present. Before we really
get into like examples and stuff of sets, just like understanding basically what they are, because I know like sets kind of has a mathematical term to it, right? But at the end of the day, all they are is representations of events occurring.
Right, I would say more like a group.
Similar events.
A collection of objects, events, things, really anything. A set is just a collection of things. And before we get more mathematical, we can give an example of a set. Like, for example, I can say that we have the set of all people such that they are police officers, right?
Okay.
So this set is a collection of people, and to be allowed into this set, you need to be a police officer, right?
Yeah. So that kind of gives you a basic understanding of what sets are, because you kind of need a condition to be part of a set. And all sets, the reason they differ are obviously like the conditions being different. And now we can also like sometimes talk about sets being part of other sets. For example, in the same example that Parker just gave, set of all police officers, if we say the set of all chief of police officers, for example, like all of the chief police officers will be police officers, right? So the set of chief police officers is in mathematics what we call a subset, because the subset will be a smaller set of the bigger set. Basically, that's the best way to put it.
So formally, when we say a subset, it basically means that every element in the subset is an element of the larger set, right? So the set of chief police officers is a subset of all police officers because every chief is a police officer, right? And so another concept we can talk about is, let's say we have the set of all people that have brown eyes. Okay, so that's pretty simple. If you have brown eyes, you are an element of that set. Okay, and so we could talk about unions and intersections, which
people with green eyes, for example. So let's say there's a set with brown eyes, and there's another set with people with green eyes. So what is the similarity? What is the difference between them? Yeah, we can talk about that.
So if you're taking the union of two sets, you're basically just saying, well, we have the set of all people with brown eyes and green eyes all together in one set. We're unifying those two sets together. But if we take the intersection, we're just taking the common elements in both of those sets. So for example, if there was a person with one green eye and one brown eye, they would be an element of the brown eye set and the green eye set. So that person would be in the intersection of that set.
And another way to think about intersections and unions are just with words. Because the easiest way to think about a union is to think about the word or. So if I say, if you have blue eyes or green eyes, that means if you have blue, you're in. If you're green, you're in. Oh, sorry. We were talking about brown. Sorry, not blue. Brown and green.
Yeah.
So if you have brown or if you have green, in both cases, you will be within the union of the sets. But the intersection is another way of thinking of the word and, right? So and, in this case, as Parker just mentioned, if you have a brown and a green eye, now the only way for that to happen is one brown, one green. Right, so then whoever has that will be part of the intersection of those two sets. So these are kind of like just mathematical terms for like kind of English statements at the end of the day.
But we're really dancing around the mathematics of it.
Yeah,
we're trying to really give examples that like anybody can relate to, right? So moving on to the next really important topic is just sentential logic, which we briefly mentioned in our previous episode when we were talking about proofs with Tom from Tom Rocks Math.
Crazy episode, by the way. Definitely
episode.
Check it out. Yep.
Basically, sentential logic is just about breaking down what every word means. So you mentioned, right, the and, the or.
Or the or.
There are also like phrases such as implications, like if something, then something else. Right? So if you are, let's say a person,
okay,
then you are a mammal.
Okay,
right?
Sure.
See,
sure.
So assuming that you're a person, that implies something else, right?
Yeah.
And we're not going to get too deep into the truth values of some of these premises, I guess we can say, but we can talk about the simple ones.
Yeah.
For example, if your premise is and we're going to talk about these sentences as just letters, right? So P and Q.
Yeah.
Right. So let's say
I think that's a pretty good ground to start off with, the P and the Q, because whenever we're going to be mentioning the words P and Q in this podcast, I think from now on, we're basically talking about two separate events, two separate statements, right? Sentences, like two things happening.
If we want to get more mathematical, we can say like, okay, we have a number that is greater than 0, okay? And so we can say P represents that condition, okay? So we have two different conditions, P and Q. And so let's say, okay, if I tell you P and Q, if I'm telling the truth right now, that means that they are both true.
Both true.
They're both true. Because if I say, yes, P and Q, but P is false, then I'm not telling the truth, because I just told you that I'm delivering P and Q, but P is false, so the whole thing is false. For that to be true, they both have to be true. That's kind of the baseline, okay? When we talk about P or Q, it doesn't matter if I give you one or the other or both, as long as I give you something.
Yeah.
Right? If I say, okay, I'm going to do P or Q, but I do neither of them, then that's false, right? Because I'm just a liar in this case.
That's a problem.
Okay. And this is a little bit more complicated one, the implication, okay? So if I say, if P happens, then Q will happen. Okay? Yeah. So if P is true, then automatically Q has to be true.
But this is, once again, if the statement holds. If the statement, and this is actually when we talk about validity, and I think we're going to get into validity a little bit right after this.
Yeah.
But if the statement is true and if it is valid, then yes, if the assumption is valid, if the assumption is also true, like if that thing is true, then whatever it implies will also be true. Right. Because the statement is true in this case.
And you have to be very careful when you analyze sentences. Yeah. Because you can the sentence can either be true or false, and the premises can either be true or false as well. And so what makes and this is going to tie in really well to when we get to proofs, right? Because, and this is also the reason why we're mentioning sentential logic, is because this is a very important phrase. And actually, this is the book that I preach all the time. If you're watching this on YouTube, you can see this on your screen right now. It's called How to Prove It by Daniel J. Validity. And if you're really interested in learning more about proofs and getting very into detail about the subject, I really recommend reading this. This is a second edition. And so I'm just going to read a quick one short passage from this. And so it says that an argument is valid if the premises cannot all be true without the conclusion being true as well. And this is, I think, a very powerful sentence that can really make you think.
And this is when we get into the validity of the statement.
And so if you're trying to prove something, you obviously need an argument. Yeah. You know, I say, prove to me this. You need to come up with an argument that will make me believe you beyond any reasonable doubt, right? So, what that sentence just said is that if I have an argument, I have premises, right? I say, okay, for example, well, P and Q are true, therefore P is true. Okay? In this case, I only had one premise. So if that premise is true, but the conclusion is false, then that argument is completely invalid. Yeah. Right? Because, for example, I can say, I'm trying to prove to you that I went to school. Okay? And then I say, well, I went to the grocery store, therefore I went to school. That is a completely,
like the conclusion doesn't really follow from the premise.
It's a ridiculous argument, right? Because it could be completely false that I went to school, but true that I went to the grocery store. But that argument makes absolutely zero sense. Yeah. So you got to make sure that the fact that you did go to school plays in with your argument, showing that you logically, I can say that I have a document, my diploma, showing that I went to school, therefore I went to school, right?
So as basically I think the sum of all of this, to summarize most of this, is the idea is for an argument to be valid, it needs to have certain conditions. The condition is the conclusion must follow from all the premises. If the premises are like all haphazard, have nothing to do with each other, and you conclude something, that just makes no sense. And I think this is also a pretty famous quote: "You can't assume less and conclude more." And I think we can talk a little bit about that, because assumptions also follow a pretty important role when we're proving things, right? Because assumptions are kind of like the key because whenever you're trying to prove anything, there has to be some baseline that you're starting off with, right? Like, let's say you're trying to prove that, X is some number, or the function behaves in a certain way. You have to assume something about the function. The function's continuous, or it's differentiable, or something about the function must be assumed for you to make a conclusion, right? Because the conclusion will follow from a set number of assumptions. And the quote I said before is, let's say you're trying to prove something else, like from what you just proved. What I was trying to say is, you can't assume less and conclude more than what you had already done. And I think we can give an example of this when we talk about proof techniques, and we dive a little deeper into just proofs. But I think for now we can just kind of say it at that, and we'll definitely talk a little more about it, though.
Right. And the example that you said, when you, let's say you're trying to show that a function behaves in a certain way, like, for example, even if you know nothing about proofs, right? If I say f is a function, prove to me that f is always positive. From the information that I gave you, there is no way for you to prove that f is always positive.
Exactly.
You need more information, and from those assumptions, like let's say I tell you that the derivative is always positive. Okay, that's not enough.
That's still not technically enough.
That's not enough. I'm admitting that.
Yeah.
But it's still more information that you can later use. Like for example, if I give you even more information, the idea of the proof is to, first of all, you take what you know, you try to dissect it, right? And you use the crucial information and the crucial points to show that, well, since all of this information, it is automatically true that my conclusion is true. So, and that's why I think proofs are very, very crucial, very fundamental
for sure
for mathematics, because mathematics is built off of axioms, and everything beyond the fundamental axioms are just basically theorems that have been proven from those initial conditions.
Yeah. And I think like the really important part about proofs, like I think just the reason they're just so important in math is just because you can really, because when you compute something in math, like even if you do a lot of practice, right? All you're doing is understanding, okay, I can solve this integral, or I can solve this derivative, or I can solve this equation, let's say, using this method. But what does that tell you about the equation? Like, you don't still know anything about what you're doing, right? And like the effect of proving something, what I think, like, for example, like there are some times when, Parker and I are just, like doing some work and we're just randomly proving things, just, proving some work, proving some homework, stuff like that. And what that does is, what I think at least that does, is it kind of hits the point home where it really makes you understand what is happening when you're proving something. Like, instead of just computing the answer or just finalizing the answer, you're kind of really understanding what, like, for example, when you take an integral, like, instead of just integrating it, with the formulae and everything that we learn, right? Instead of, we take, like, rectangles, we take individual rectangles, we sum them up. Like, you're getting a better understanding of it with proofs. And I think that's like kind of where proofs are definitely very, very essential in math.
And I think it was really interesting last year. I don't think we proved like Riemann integration. But we went through like some. I think we were presented the proofs.
Yes, I believe
why Riemann integration works, and that was definitely like seeing the mechanics behind what happens when you integrate a function. Like, why is it when you write a squiggly line, it gives you the area under a curve, right? Like. Well, not necessarily the area. Is it the weighted area? Like, it could be negative as well.
Well, it can. It depends on where it is in the graph.
It's the quote unquote area, because area can be negative, but geometrically that
area
doesn't
cannot
make
be
sense.
negative. Exactly.
Right. So this next little segment is going to be more.
I think we can still. I think we can still continue a little bit more on just logic and talking about special types of logic. For example, a tautology. So a tautology is a type of statement that always holds true no matter what the premise is, right? Like, I think I'm getting
it's like a tautology is basically, it can be a premises, but it's basically useless because it is always true. Like,
so basically the conclusion is always true.
Not necessarily.
Or is it the premises always implies the conclusion?
If you remember that sentence that I read, I said all the premises cannot they cannot all be true without the conclusion also being true. But if the premises is always true, then that means you're gonna get sometimes the conclusion is gonna be false, but the premises is still true because it's always true, right? And so that's gonna be an invalid argument. For example, an example of a tautology is, if I want to get a little bit more mathematical, I can say, well, I either want an x that is greater or equal to 0, or an x that is less than or equal to 0. That is always true. No matter what real number you pick, that is always going to be true. So using that as a premise is never going to give you any information because that sentence is always true. Similarly, we have contradictions. which are premises that are always false, which also don't help you, right? Like if I want an x that is always greater than 1 and is always less than -1, that is never going to happen. And so that premise is always going to be false. Mm-hmm. And sorry, I think I made a mistake when I was talking about tautologies. I said one or the other.
Yeah, you meant and.
Oh no, that's right. No, never mind. I didn't make a mistake because the and is for the contradiction and the or is for the tautology.
Or it's for the tautology. Right. Oh yeah, true. Yeah. So continuing a little bit more on logic, I think we can talk about quantifiers. I think quantifiers are definitely something that we can talk a little bit about today. Yes. So quantifiers are
quick throwback to first year.
Yep.
I'm sure we were absolutely making a fool out of ourselves.
Oh, yeah.
while we were dealing with our first unit in calculus, which was logic and proofs.
No, I know the first one was.
Yeah, it was
logic. Oh, with logic and proofs. Yeah, with logic and proofs. Yeah, true.
And I think quantifiers without a proper introduction is hard to wrap your head around. Mm-hmm. But hopefully with our little simple explanation. Maybe it'll be easier to understand.
Yeah.
So we have like two global quantifiers. No, sorry. Global is the wrong word.
Existential quantifiers, right?
No. Global is for all. Existential.
Yeah, existential is that there exists. Exactly.
But I meant there are two like important ones.
Yeah, important.
There's also a third one that we'll present briefly. But so the first one is for all, and it is an upside down A. And then there is the existential quantifier, which is the there exists, and it's a backwards capital E.
So it's kind of like an E mirrored on itself, yeah.
And so when you say for all, and then something like let's say for all x,
but you have to say for all something in something,
right?
Yeah. You also have to specify.
Let's say for all x in the real numbers, something, right? You want to add a condition, right? That means that the following proof has to work for any x that you pick. Mm-hmm. Okay, and this is where the language kind of becomes a little complicated, because when we say for all and for any,
definitely
it is the same thing.
It sounds different, I know, because the first time I heard it, I was very, very confused. Because for all sounds like it works for every single one of them, right? And for any, it just sounds like it'll work for anyone, But at the end of the day, they mean the exact same thing, because even for any, but the idea behind that is you pick any x, any number, and it'll work. That means technically, in mathematical terms, it should work for all of them.
And so
that's kind of just a way to say it.
What I think about when we do like a for all statement, I think about picking an x and then showing that whatever is true, and then. All right, okay, sorry, the video just cut out, but
sorry,
we're
back. We're back. Okay, so where were we? We were
talking about the for all.
Yeah.
Right. Wait, is it recording?
I believe so.
Yeah, it is recording. Okay. So we were talking about the for all quantifier. So what I think about is you pick one, but this is not.
No, you don't pick one.
No. I mean, I meant you pick one, but it represents
the whole
set,
thing,
right? And remember the element, when you say for all elements, it has to be in a set, right? So if I say for all x in the real numbers, then what you're going to prove has to work for any x in the real numbers. So
basically any real number.
So when you start your proof, the first thing you should say is just, let x be a real number. And then you also use that as an assumption, right?
And then that's where assumptions again come into
which is a piece of information that you could use at any point in your proof. And let's say, for example, you're trying to prove that you're trying to prove something for all x in the positive natural numbers.
Okay. Then
you can use the fact that that x is never negative, and also x is always an integer. It's never going to be a rational number. So yeah, I don't think we're going to get too technical into what to do after that.
But what I think we can definitely touch up on is the other quantifier.
Definitely.
The existential quantifier, which is there exists. So just like we were talking about a for all. So for example, if we say for all x in real numbers, that means we're taking any real number and this should work. But the other quantifier that we're talking about today is that there exists. So there exists. Let's say we say there exists an x in the real numbers. So what that means is that the statement that follows that there exists. So usually the way we write it in math, again, this is just math lingo. We do there exists an x in something such that something else. The such that is very mathematical, very important when you're writing a mathematical statement. Like you will literally, like we got marks deducted because we did not include a such that. So
it's in fact correct.
It's definitely an important part to your statement. But basically, the idea is the there exists quantifier means that there's simply one number in all of these numbers, or one value that it can work for.
That's right.
I'm not saying it can work for.
So essentially, it has to work for at least one value.
Can, yeah. As
so
I said.
There could be an infinite amount of values that work, but the point of your proof is just to pick one value that works and show that the condition is being satisfied, or whatever you're trying to do. The important thing to note is that it is not unique. There can be two. There can't be
one.
zero.
Can't be zero. That's the main idea. At least one number such that this statement holds, right?
And notice how I said it doesn't have to be unique, and that is kind of the third quantifier, and it's the existence and uniqueness quantifier, and it's a there exists, so backwards capital E with an exclamation point. And what that means is that there is one element and only one element that satisfies the condition. So if you can find two elements that satisfy the condition, then your whole thing is false. If I say there is one number that can be divided by 3, but I say, well, 6 can be divided by 3 and 9 can be divided by 3. So obviously my
can be divided by 3 is the wrong thing to say, because every number can be divided by 3. It returns a whole number. Returns a whole number when divided by 3. There are a lot of numbers. Yeah, but basically, that's the point of it.
Or I think the way to say it is 3 divides that number.
3 divides that number. That's a better way to say it.
Yeah. So since there's more than one, then automatically my statement was false.
Mixing quantifiers.
This
For all and there exists in the same statement. So also really quick though, before we get into this, I think the easiest way to think about these quantifiers, like for all and there exists, is just to say it in English.
Yeah.
Like at the end of the day, if you say it and if you really understand what the statement is trying to say, a lot of times, like, it'll just make sense. Like, some statements that, like, for example, we're actually going to give 2 examples that I think are pretty important. And if you really understand quantifiers, like, you'll be able to immediately deduce what the answer is. Yeah, immediately.
Definitely.
But, if you don't, you'll definitely have a time to think about it. But I think it's quite important.
Yeah. So, and we're just going to touch on these examples briefly because it would really help to write it down and look at it for yourself. So we're not going to really just talk about it until we feel like everybody understands. We're just going to mention it, and then hopefully, you can go home,
research it a bit,
try it out on your own if you feel so inclined. But the first example is that, for all x in the real numbers, there exists a y in the real numbers such that x is greater than y. Now let's decompose that a little bit, okay? So I said, for all x in the real numbers, this means that for any real number that you pick, okay? It could be 1 million, it could be negative pi, okay? Yeah. It could be anything. For any, there exists a different or possibly different number. It could be the same.
A y. Some kind of y.
It's just some number y in the real numbers. And what I'm trying to show is that x is greater than that y. Now that is true, and it can be proven pretty easily, actually. But so the first thing you want to do is say, well, just let x be a real number, and then you want to pick a y that works for that x. Now that can be kind of confusing because in your head you might think, okay, well, there's not one single y that can be less than every single x. And we will get to that line of thought
we're gonna
after
get to that
this
in a
example. But remember what I said when we're dealing with the for all quantifier. When you're dealing with the for all quantifier, you pick an arbitrary x, and then when you're saying for all x there exists one y, you pick one y that is convenient for you.
Exactly.
Right? You pick a y that has to do with your x. So for example,
the easiest
here's
way.
A good example. If I pick y to equal x minus 1.
Easiest example.
Right? So this works, right? For example, if I say x is equal to 100, that means y is equal to 99. In that case, x is greater than y.
Yeah.
Right? And have a field day with it. Pick any number you want. The y that I chose shows that there exists a number that will always be less than any number you pick.
Because in quantifiers, a very important thing, and we're gonna, I think, really get the point home with the next statement. But one really important thing with quantifiers is the order of the quantifiers. Yeah. So in this case, as Parker mentioned, it was for all x, there exists a y. That means for any x that I choose, there's a y that's smaller than the x. Well, yeah, obviously. Like, if you put it in terms of English, it's so obviously true. Like for all numbers, for any number that I choose, there's a number smaller than it. That's basically what it's saying, which is so obviously true.
Yeah.
But once again, if you put it in terms of the mathematical statements, you can definitely get confused.
Yeah. And so the other example.
Yeah, this is where I think the other example is a lot more interesting.
Right.
Where it says there exists a y, or we can do x. There exists an x in the real numbers, such that for all y, right, x is greater than y.
And it's implied that y is in the real numbers.
Yeah, y is in the real numbers. So if there exists an x in the real numbers, such that for all y in the real numbers, x is greater than y. Now, quick notice, we switch the two quantifiers.
That's right.
Instead of for all there exists, it's now there exists for all. So let's break this down.
Yeah, if you remember what I said about the existential quantifier, you're trying to show that there is at least one value. So you can say, okay, let y equal this, okay? And then show the rest of the sentence, okay? And just a little spoiler alert, this is not true.
It's false.
Okay? It is completely false. And the reasoning is because
English.
If you set one value for y, you say, okay, let's say y is equal to 5. We're trying to show that 5 is greater than every single number,
one. Yep.
Right? Notice how the order changes everything.
Yep.
Before we said any number you pick, there's one number associated to that is always going to be less than that. That is quite trivial, right? Now we switch the order and we say there is one single number that is greater than all the other numbers,
which is clearly false.
Which is impossible. You can pick 10 billion.
10 billion and 1. There's always some number that's bigger than another number. Right?
And I really want to touch on proof techniques now because
to be honest, we're really we're so excited about what we're talking about now. We definitely want to talk about proof techniques.
So I will show you how to prove that is false, and it is quite easy. Okay, so showing that it's false, what you can do is show that the opposite is true. Because if you say, well, for example, I want to show that x is positive.
Yeah.
If I show that x is not negative, then I show that x is positive, right? Yeah. So if I want to show that there can't exist one number that is greater than all numbers, well, I do the opposite, right?
So you just kind of so the opposite is kind of with the quantifier is switching the for all to there exists and there exists the for all. So that's basically the idea. So the negation in this case, right? The negation of the statement, or a statement filled with quantifiers, is just going to be switching up the quantifiers. Now, obviously, it is more complicated than that. It's not just that.
Yeah.
But for the example that we're giving, that y is just greater than x or x is greater than y, you can just switch it, and statements technically still holds.
So you switch the quantifiers, and when you switch the quantifiers, that's exactly the example that we gave
before
in the beginning, and
the for all there exists.
Yeah, we showed you guys the logic as to why that's true, and so you showed that the opposite is true, which means that it's impossible that the original statement can also be true. So that's how you would prove a negative. Yeah, a negation.
A negation.
Right.
Yeah, so I think just understanding quantifiers is a very important key to understanding the language of math, right? Because like once you can read quantifiers and once you can understand quantifiers, like I'm not even joking. There are some problem sets that obviously or for like some homework that we have that has a lot of these quantifiers, and obviously if we had not studied this in the first year, I don't know where we would be right now. Nope. I don't know where we would be right now. But we're reading these statements and we're just, we're understanding what the statements are saying on the first read. Like that's the idea. That it gives you the ability to read and understand math. And I think that's the most powerful ability.
And I also feel bad for a lot of people because if you don't know, at U of T, there are basically 3 streams of mathematics. There's the computational, half proofs, and then just the full proofs, which
analysis,
is the
full analysis course.
Full analysis. And so Rehan and I are both in the half computations, half proofs. But there are people that in first year were in the computations stream and then bumped up to the proofs / computation.
So they had never seen a quantifier. They had never seen connect. Like they had never really seen if-then statements.
Yeah.
Like, yeah.
That's right. They've never seen any of this sentential logic and proof things that we're talking about in this podcast, and I can't imagine being in that situation.
Oh no.
I think the level at which we are dealing with these mathematical statements is way beyond a beginner level.
For sure.
Which is what you would be coming into
if you just did the computation.
If you did the computational streams.
Because I think, to be honest, like proofs is literally a different. Yeah. It's a different thing than computations. Because you can be good at computations and just be terrible at proofs, or the other way around. Because a lot of people, I guess you can't really be the other way around. You can't. If you're good at proofs, you're probably good at computation. That's actually true.
Yeah.
But you can definitely be good at computation and be bad at proofs. Yeah. Definitely people like that. And I think the thing about proofs is kind of similar to computations, where if you just practice it more, you just get better.
Yeah, and you can be bad at proofs, but it's not because you're just inherently bad at proofs.
Yeah.
It's just because it's a whole other language that isn't presented
exactly
to high school students.
Exactly.
And I in my opinion, was very poorly presented to us in first year. We were kind of just thrown into the pool.
Yeah, that's why, to be honest, like going into a bigger picture, that's why I think nobody can really be bad at math. Because it's like you're bad at Spanish or you're bad at French. Like you can't be bad at a language. You just don't know the language well enough yet. Yeah. Like you just gotta have to learn the language. That's all.
Yeah.
Like it's that's basically the idea behind it.
So briefly,
right.
I just want to briefly go over other proof techniques based on the nature of the
statement,
the statement you're trying to prove.
Yeah.
Right. So if you're trying to prove something that is P and Q, basically you just need to show that both of them are true.
Yeah.
Because, right, as I said before, if one of them is false, then P and Q is false. So if you're doing P and Q, show both of them are true. Boom, proof done.
Proof done.
If you're trying to do a P or Q, then you just need to show that either prove that P is true, case 1, and then case 2, show that Q is true. And so when you put those together, P or Q is either true at one time or the other. Or you can assume that P is false and show that Q is true. Because if you think about it, that is the necessary condition for that statement to be true. If one of them is false, the other has to be true. Or if the other is false, the first one has to be true. So that you can do that. If your statement is just P, you're trying to show one thing. What you can do is assume it's false and show a contradiction.
Yeah.
For example,
contradictions are actually very helpful in math because the thing with proving something to be true is that you must prove that it exists for any, like for I mean I guess it completely depends on what the statement says, But if you're trying to prove something is true, you have to prove that it holds for any variable chosen. But if you're trying to prove a contradiction, you just have to show that it doesn't work for just one example.
Well,
if you're trying to prove a contradiction,
that depends.
like a counterexample.
Right.
Yeah, like if you're trying to show that this proof is just false. The easiest way to show that a statement is false is just by proving one counterexample, right?
Right.
Because if a statement has one counterexample, no matter how good the statement is, even if it works for every single thing that you can think of, if there's one example that it doesn't work for, it's false.
And that's a very powerful
it's a very powerful
tool that you can use, because sometimes your statements can be very general and it could seem like very, very difficult to show that it's false. But if you just say, well, okay, I can think of one example and that example doesn't work, then automatically, boom.
Exactly.
You've shown that the whole thing crumbles under that one counterexample.
Exactly.
Other than that, the if-then statement.
Oh, yeah, that's an important one.
If-then,
the assumption.
You just assume the if is true and show the then is true, right? So you use the information in the if, which is called the hypothesis.
No, that's not the hypothesis.
The conclusion.
If something, then something else. Isn't it
hypothesis conclusion?
I swear hypothesis means something else.
Supposition.
Okay, I think we're both confused. Sorry.
Whatever. It doesn't matter. Just the first statement, you assume that. You use the information in that statement to show that the conclusion is, or the implication is true. I think we're getting confused with...
Yeah, sorry. Parker was right. It is hypothesis followed by conclusion. Sorry, I was wrong. I thought it was... I don't know why I thought hypothesis was maybe something else. But yeah, so if hypothesis, then condition. That's the idea. And yeah, and I think you already said, yes, assuming the if part, assuming the hypothesis.
I guess conclusion.
Yeah, conclusion.
Not condition. You said condition.
Oh, sorry, conclusion. I meant conclusion. Sorry, not condition.
Okay. Sorry. Also, there's another way. I think this is a little beyond the scope of this podcast, but to show an implication, you can also prove a P or not Q.
Or not Q. Yeah, no, P.
So P implies Q is P or not Q. You can show that, and then you could use the techniques to show an or statement.
Yeah,
but I'm not.
That's a little. That's just a little.
I'm not going to explain why.
Something that I'm kind of. I think we kind of forgot to get to is the complement and the idea behind complements.
I think we can do another.
We can maybe do another one because I was thinking of because I mean we're both looking at like the stuff where. We have to talk about today, and we have so much more stuff than we could get through. Because I mean, I think this is a pretty cool topic to talk about, especially for people who say that, hey, I'm in high school and I know that I'm going to be dealing with proofs soon because I'm interested in math and physics. Because a lot of people like that email us, but they're in high school and they have no idea what this is. So we're just trying to help you guys out. And I think I think we would have benefited from especially a book like that, how to prove it.
If I would have had this resource in high school, I would have loved my life in first year.
For sure. It's definitely a very, very helpful book. Yeah. So, just like small things like this definitely help you get through your first mathematics year.
Yeah, so I'll definitely link where you can buy this book in the description.
Yep.
And I guess we're already at 43 minutes. So we're going to end it off here.
We're going to end it off here.
So... yeah, this has been episode number 36, live podcast.
Yep.
Make sure to watch on. I don't even think we mentioned this in the beginning.
Yeah, I was actually okay. So we were 5 minutes in, and I was thinking about it, and I'm like, we didn't mention that this is a YouTube video. So I don't know if people are gonna know, but okay. So I guess we can kind of just. Yeah,
I mean, it's
fully
fine.
Forgot.
It's fine. We're gonna just follow us on Instagram.
Yeah,
where we will let you guys know that this is a YouTube video. This is being recorded live.
Yep.
And we always love the live podcast.
We love them.
Great experience. Follow us on Instagram at math.physics.podcast. Email uoft.math.physics@gmail.com.
Yep.
Follow us on Spotify, on Apple Podcasts, on
any
YouTube.
Any platform. The platform that you're using. Follow us on there.
That is absolutely correct.
Yep.
So this has been episode number 36 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
See ya.